Okay, so yeah, once again, welcome to the new semester on representation theory. So we'll begin with multilinear algebra, but maybe less fixed notation about our vector spaces and so on. So let K be a field. So usually we will think of it as C, complex numbers. So many of the definitions, all the definitions will work over arbitrary field, but some of the results will work only on C, or you would need at least characteristic zero field, yeah. And in some cases, and for some results, you also need that field to be algebraically closed. So we will work, but we will think of it as complex representation, meaning our vector spaces will be complex number. Our K will be C. Yeah. So now, if you are given two K vector spaces, P. Yeah. So as you can see, the grammar is already off. B K vector spaces. A map phi from V to W is called linear if this happens. Yeah, so so this is the definition of linear maps, and we'll deal with mostly finite dimensional vector spaces, yeah, in representation theory. So so most of reasonable representation, even the group sometimes, so even in the advanced, so next course or higher, so other courses on representation theory, the groups may be infinite, but usually the vector spaces are considered to be finite dimensional for most of representation theory. So there are infinite dimensional representations, but they are less studied. Yeah. So so this is a linear map. Similarly, if you are given n vector space, you can get if you are given two vector space, you can get a bilinear map. So bilinear map means it should be linear in both variables. So if you fix a vector in V1 and you think of this function phi V1 comma dot, so that dot is the running variable. So it's a map from V2 to W. Then it should be linear in. Then it should be linear again. Yeah, so it should satisfy this property. And similarly, phi dot V2 is linear. Yeah. So and multilinear means the same thing. V1, it's a map from V1, V2, V1 plus V2 plus Vn, and then it should be linear in each variable. Yeah, so that is what a multilinear map looks like. So so we will yeah, so maybe I'll start with tensor products. So did I define tensor product for you guys? Or do you know tensor products from earlier course?
I don't think we did it in algebra 3. You might have mentioned it and some basic properties, but not proper.
So I didn't define tensor product in algebra 3, is it?
Yes, sir, most probably. We just did those exact sequences and some basic properties.
Yeah, so I may have just done some modules, yeah, exact sequences, but not tensor product, yeah. Okay, yes. So maybe, and you haven't seen it in, you couldn't have seen it in any other course, yeah. So maybe I'll do some tensor product, yeah. So the definitions are, yeah, it's algebra 3, yeah. localization of modules. Yeah, the advantage of online teaching is I can go back. Linear maps, yeah. So I haven't done, yeah. So so maybe I'll do some tensor product. So the thing is, the definitions work for any R module, yeah. So you don't have to, so you don't have to do it for vector spaces, but you can do it for any R module. So if R is a ring and M is an R module, so if R happens to be a field, then module is same as vector space. That you know, yeah. So yeah, but I'm thinking whether I should do it in generality, or let's stick to this case. Yeah. So maybe yeah. So maybe I'll do for two variable. Yeah. So maybe I'll do it in somewhat of a generality. Yeah. Tensor product, because it may be useful for your other courses. Yeah. So. Yeah, so let R be a ring. I mean, the effort is same, so that's why I'm thinking it doesn't help me, but we'll concentrate. So definition will be for general R module, but we'll the properties will only worry about vector spaces. Otherwise, I mean, a week will go away on tensor products. Yeah, and M, N, B are modules. So ring here means maybe you just, I mean, we will be working on field, but this commutative ring, I mean, okay, with unity. So, so nicest possible ring. I mean, the definition may work slightly more generally, but we don't want to worry about that. Yeah. So, tensor product is defined in some weird way. So it's defined using some universal property. Yeah. So an R module T for tensor product, let's say, is together with sorry, with a bilinear map phi from M cross N to T is called the tensor product of M and N if the following holds. Yeah, if the following holds. So the following is the universal property. Given maybe this I can put it in the next line. Given any bilinear map given any bilinear map C from M cross N to some other module, I don't know, and maybe A. Bilinear meaning R bilinear, sorry. So bilinear makes sense, yeah. Like that was K bilinear. Here it is R bilinear. So same definition. Yeah, A is in R's and B1 and B2 are in M and N respectively. Yeah. So given any RB bilinear map from M cross N to A, where A is an R module, that exists a unique R linear map theta from T to A such that this C is composition of these two, yeah. Such that C is first you apply phi and then apply theta. Yeah. So if you want to put it in a picture, so you have a you can write it as a commutative diagram. Yeah. So M cross N to T, and you have A. So this is your C, and this is your. So this phi is the part of the data. Yeah. So tensor product is tensor product consists of this bilinear map also. Yeah. So it comes with this bilinear map M cross N to T. And so you call T to be tensor product if you can find all given any bilinear map, you can find this theta. Okay. So this is what tensor product of two R modules look like. Yeah. So of course I've defined it, but it's not clear why such a tensor product exists. Yeah. So yeah. So maybe I'll. So it's the proof is not difficult. Yeah. So the idea is to take the free group on free R module on M cross over M cross N, the set M cross N, and then you quotient out by all the bilinear relations, and that will give you a that group that R so that will be a R module, and that will be the tensor product, and then you prove that it has the universal property. Yeah. So yeah, so maybe okay. I think I have it somewhere in the notes, so I'll just do it from there. Yeah, tensor product of modules. Okay. So instead of rewriting everything, it might be and simpler to do it from. Yeah. The notations are, so in spite of doing it independently, I have the same set of notation. Yeah, good. So I'll put it in the notes as well. Maybe I'll keep a copy of this on the notes. Yeah. So as I said, the proposition says T exists and is unique up to isomorphism, and it is denoted by M tensor N over R. So if you are doing, so this is from my algebraic geometry course. So I don't know, this may not be covered. So not everyone covers tensor product in algebraic geometry, but so it's not guaranteed that this will be covered in your algebraic geometry course, but it may be, yeah. And then maybe the guy can go a little faster, skip if all of, yeah, sorry, may not skip. But anyway, so this is, So T exists and is unique up to isomorphism and is denoted by M tensor N. Yeah. So as I said, so first uniqueness is pretty straightforward. It follows from this diagram chasing, yeah, and construction is the main gist, yeah. So suppose there is another guy which is unique. Unique meaning unique up to unique isomorphism. Yeah? So tensor product exists and is unique up to unique isomorphism. Yeah, and then it will be T will be denoted by M tensor N. So this is the proposition. So first we will prove that T is unique up to unique isomorphism. So suppose T prime is another tensor product. So right now we don't know whether such a thing exists, but suppose there are two of them. Yeah. And then we want to show that there exists a unique isomorphism T to T prime such that this happens. Yeah. And that will prove the uniqueness part of this proposition, and then we will do construction. So by universal property of T, what happened? Okay, somehow it skipped a few pages. No, sorry. Yeah. So yeah. So T prime be another tensor product, and by universal property of T, so you know phi prime is bilinear, yeah, because T prime is another tensor product, so it comes with this bilinear map. So by universal property of T, there exists a unique map alpha from T to T prime, which will make this diagram commute. Yeah. That means phi followed by alpha is same as phi prime. Yeah, but T prime is also tensor product. Yeah, so it also has a universal property. So you can make this diagram, to T, and then you can say there exists a unique alpha prime from T prime to T, which will make this diagram commute. Yeah. So alpha prime, so phi prime followed by alpha prime is phi. So you get this one and you get this two. Yeah. And now think about alpha followed by alpha prime. Yeah. Alpha followed by alpha prime is a map from T to T. Yeah. And of course, identity is also a map from T to T. Yeah. And T has the universal property. Identity is linear, and it will of course make this diagram commute. And since there is a unique map from T to T, which will make this outer diagram commute. Yeah, that tells you that alpha followed by alpha prime is actually the identity map. Yeah, so alpha prime composed alpha is identity of T, and similarly you can show that alpha composed alpha prime is identity of T prime. Yeah, so alpha is an isomorphism, and uniqueness of alpha is clear. Yeah, because that is part of the definition. Is this okay? This proof of the proposition, does the uniqueness of the tensor product?
Yes.
Yeah. Yeah. Okay. So now the existence. So existence, as I said, you look at the free module over M cross N. Yeah. So that is how the construction is. So F be the free R module over the set M cross N. Yeah. So you think of it as M cross N. So there are many copies of R, same as the number of elements of M in M cross N, and for each tuple M comma N, you sort of label that copy by R M N. Yeah. So this is a free module. Of course, you can take the inclusion map. Yeah. So this is not R linear. This is a set map. Yeah. So you send m comma n to 1 times m comma n in this free module. Okay. So we will once we quotient out f by the right guy, this will become R bilinear. Yeah. So we don't really want an R linear map from m cross n to R tensor product. We want a bilinear map. So that's why we will have to do something to f. Yeah. So what is this quotient? So you consider the submodule generated by these relations. So you sort of force bilinearity by going mod all the bilinear relation. Yeah. So Q is the quotient map from F to F mod this submodule generated by m comma n1 plus rn2 minus m comma n1 minus r m comma n2. Yeah. So what do we want in our in this module which we are in this quotient module? What we want is that for each m, n1 plus rn2 should be same as n1. So the image of n1 plus rn2 should be same as image of n1 plus image of r times n2. Image of n1 plus r times image of n2. Yeah, that is what we want. So that's why we are quotienting out by this this guy. Yeah. And similarly, in the second, to force linearity in the first variable, you have to put these guys in. So if you consider the set of these elements, they won't be form a submodule. So you have to take a submodule generated by this in this free module, and consider this quotient. So that is we will show that we will call it T, and we will show that this is the tensor product. Yeah. So first, we also have to say what the bilinear map is. So bilinear map is this Q composed I. So you first apply I, get to F, and then apply the quotient. Yeah, and what we have done will ensure that this phi is bilinear. Yeah. So that was the reason to quotient out this thing. So let's just check. So want to show that phi is bilinear. And we want to show that it has the universal property. Okay. So let's call K to be the kernel of Q. So K is basically precisely this submodule, yeah, which we have quotiented out. So it's the same guy. Yeah. So the submodule which is in the denominator is precisely K. Okay. So now let's take consider phi of. So we want to show it's linear in the second variable for all m in m. Yeah. So you consider phi of m comma n1 plus r n2. Yeah. So yeah. So this is same as Q composed I of m comma n1 plus r n2, which but I does nothing. Yeah, it just sends it to I of m comma n1 plus r n2 is just Q of that pair. Yeah, I just sends it to 1 times that guy. Yeah, in the free module, and Q of m comma n1 plus r n2 is basically the image of this. So it's the quotient map. So it's the same coset. Yeah. So coset representation. But m comma n1 plus r n2 is same as m comma n1 plus r times m comma n2, because the difference lies in the kernel K. Yeah. So this difference, we have forced it in the kernel. I mean, these are precisely the generators of K. Which is same as phi of m comma n1 plus r times phi of m comma n2. Does this make sense? Yeah. So this is the reason we were quotienting out by this guy. Yeah, is this clear?
Yes.
Yeah, yes, sir.
Yes, sir.
Yeah. So, are there any questions at this point? Anyone? Rishika, Arun, everyone is fine with it?
Yes, sir.
Yeah. No.
Yes, sir.
Okay, good. So, yeah. So this is how this. Yeah. So this is how you get that phi is linear in the first variable, and the same thing will tell you that is linear in the second variable. So you get that phi is bilinear. Yeah. Now the next step is to make sure that it satisfies the universal property. So the reason it satisfies is because we took the free module. Yeah, we started with a free module. So free module has some universal property. Yeah, it is the biggest sort of module from where you can get maps and so on. So let's see from M cross. So we want to now prove that it has the universal property. So C be a map from M cross N to A, which is R bilinear. Yeah. So we want to construct this theta from T to A, and we want to show that it's unique. Yeah. So it's the theta composed phi is C. So what we'll do is, so as you know, giving a map from free modules are easy. Yeah, you just have to say where the basis has to go. Giving a map from arbitrary module, so if there are relations, you have to make sure the kernel has to go somewhere and so on. But the advantage of giving a map from free module is you just tell where the bases go, and then then it is fixed. Yeah, so the rest of the elements you just is going to be a unique linear combination of basis elements, and you just decide where, and then linearity forces where it has to go. So we will first cook up a map. Instead of theta, we will give a map from F to A, and then we will show that it descends to T. Yeah. So where should M comma N go? So it should go to C of Mn. Yeah. So you define theta tilde from F to A as M comma N should go to C of Mn. So once you have said where the basis element goes, then you know where every other element has to go. So summation R, so any arbitrary element of F looks like summation Rmn M comma N, where only finitely many Rmn are non-zero. The rest must be zero. That is how the direct sum of this. That is how this free module looks like. Yeah, this direct sum means exactly that. Yeah, only finitely many are non-zero. So I hope you remember these from the. So direct sum of modules I must have discussed. Did I discuss direct sum of modules?
Yes.
Yeah. Okay. Okay. Yeah. So where was I? Yeah. Theta tilde. Yeah. Okay. Good. So this is how you define theta tilde. Now we want to show that we actually want to construct a map from T to A, not from F. But T is a quotient of F. Yeah. So and quotient by that that submodule K, which is generated by all that bilinear relations coming from bilinear to force bilinearity. Yeah. So all we have to show is that kernel of theta tilde contains K. Yeah. So once we show that, then of course there's by first isomorphism theorem we will have that it will induce a map from T to A. Yeah. So note that C is bilinear, so that is where we will use the fact that C is bilinear. Yeah. So theta tilde of this guy is just C of this guy, yeah, because that is the definition. Theta tilde of and the sum is basically, you look at the coefficients, you put C in front of, yeah. But since C is bilinear, that tells you that this is precisely 0, yeah. So what does that tell us? That tell us that every generating, so the generating set of K, K was generated by those relations. So generating set of K is mapped to 0 by theta tilde. So that tells you that the whole of K is mapped to 0. Yeah. So K is contained in kernel of theta tilde, and hence, So I mean, this first isomorphism theorem doesn't imply K is contained in kernel theta tilde. This the next statement. So by first isomorphism theorem, there exists theta from T to A such that theta composed Q is theta tilde. Yeah. So I hope I have done. Did I do this first isomorphism theorem?
Yes.
Yes.
The extended version.
Yeah, for modules I've done this first isomorphism theorem. Yeah. Yeah, linear maps isomorphism theorem. Good. So yeah. No, I was in yeah, okay. Yeah. Okay. So we get this map theta from T to A, yeah, and in fact, yeah, so this doesn't prove unique. So the first isomorphism theorem says there is a unique theta which will make this diagram commutative, but that doesn't prove the uniqueness of theta. You still have to prove the uniqueness of theta, yeah. So you have to, because you started with some map and then theta tilde and then constructed theta. So you can check that theta is unique, okay? Because it's defined using C in some sense, yeah. So you just have to check. So if you have another theta prime, let's say from T to A, which will make this diagram commute. So if you have another, yeah, so maybe since this is the first class, maybe I should check here, yeah. So suppose theta is this map T to A, yeah, which makes this diagram commute M cross N. So there is the C, and then there is this phi, yeah. So now, and maybe I'll write theta here. Yeah, so now suppose theta prime is another guy which does this. Yeah. So so we want to show that theta and theta prime are same. Yeah. So you maybe it's not too bad. Yeah. So T of course is a quotient of F. Yeah. So yeah. So yeah. So I'll and then there is and F is also sort of made of M cross N. So there is a map from I from M cross N to F. Yeah. So we have this picture. So theta of so a typical element in T looks like theta of so summation Rmn M comma N bar. Yeah, this is how a typical element of theta looks like. So actually, if I show, so it's generated by M comma N bar. Yeah. So if I show that theta of M comma N is same as theta of M comma N, theta prime of M comma N prime, then we are good. Yeah. So maybe. Yeah, so this is these generate T because these generate F and T is a quotient of this. Yeah. So theta of m comma n bar. So if we show that theta and theta prime agree on the generating set, then they must be the same. So what is theta of m comma n bar? This is same as by definition. This is so this is theta of q of I of m comma n. Yeah, I of m comma n is one times m comma n, and q of that is m comma n bar, and this is what you get. Yeah, and we know that theta this is same as theta composed c phi. Yeah, so this is theta composed phi by this this thing which is same as c. Yeah. So theta of m comma n bar is just c of mn. Yeah. And this is same as theta prime of well, theta prime of m comma n. What is theta? So what is theta prime of m comma n bar? Well, m comma n bar is an element of T, and so this is theta prime composed q composed I of m comma n. Yeah, and so I have to use the fact that theta prime composed phi composed theta prime is q. Yeah. Yeah, so phi, what is this map? Phi is phi also we constructed. Yeah. So what is this map phi? Phi is this q composed I. Yeah. So phi is this map. Yeah. So phi is q composed I, right? So and we showed that phi is this map. Yeah. So so this is sorry, here it should be theta prime. So this is theta prime composed phi of mn. Yeah. And since theta prime makes this diagram commute, that tells you this is just c of m. Yeah. So that tells you that both theta of mn bar and theta prime of mn bar are both cmn. Yeah. So this tells you that theta equals theta prime, since mn bars for m in m and n in n, the set generate T. Okay, so that that completes the proof of uniqueness as well. Okay. So so that says that tensor product exists and is unique. So the constructions, the good thing about this is that when people use this tensor product, they don't really use the construction that much. As you can see, the construction is very, I mean, it's not artificial, but to construct, you have to pass to a very big free module, yeah, over m cross n, and you have to quotient out by a very big module. So it will not give you, I mean, the end result happens to be nice, but the objects you are using to construct it is not nice. I mean, F is a free module over infinitely many guys and so on. So it's not really a nice, so the objects involved in constructing are not nice modules. Yeah. So what is useful is this universal property. Yeah. So the definition you should remember. So this definition is more useful than the construction. Okay, that's why it's not defined using the construction. Yeah, it's defined in this particular way. So you should remember the definition, and this universal property is what allows you to allows you to prove some basic properties of tensor product, yeah, which we will maybe I'll go through a little bit, and then these and they allow you to compute tensor products of modules and so on. Yeah. So for vector spaces, it's pretty straightforward. So I don't know if I should do some basic properties or not. So maybe I'll state some basic properties, yeah, and I'll let you guys figure out. So I guess I can go through some of it, but the proofs as well. But maybe I'll just state it. Yeah, I don't want it to go too much in that direction. Yeah, I don't want it to be algebra course. So I'll state some basic properties and then I'll move to vector spaces. Yeah. Okay. Yeah. So so there are some. So maybe. So just to give you a feel about the tensor products are reasonable objects, though the construction is not. So for instance, if you take R to be Z and M to be M and N to be Z, then this tensor product is just Z. Yeah, it's not something crazy. Yeah, though I mean the construction says you take a free module over Z cross Z, which is God knows what that is. Yeah, so it's a very big module, and you quotient it out by some crazy thing, and eventually you get what you get is Z. Yeah, so you don't get something completely crazy. Yeah. So the way one proves that this is Z is the tensor product of Z cross Z. So I have to tell you what the bilinear map is to say that this is a tensor product. So the bilinear map is A comma B going to AB. Yeah. So this is the tensor product. Yeah. So this is the tensor product. Okay. And so you show that this satisfies the universal property. Okay. So if C is from Z cross Z to M is a bilinear map, and theta, then one can give a map from Z to M, which will make this diagram commute. So so to give a map from Z to M, you just have to decide where one goes. Yeah. So you have to make this diagram commute. Yeah. So of course, phi of 1 comma 1 goes to 1. So you send 1 to phi of 1 comma. Then theta of A will be C of A1. And then you can check that all the other things are forced. Yeah. So it does. So theta. So you have to check that theta compose C of AB is same as C of AB. Yeah. So theta compose phi of AB is theta of A times B, which is C of AB, which is B times C of A comma 1, because C is linear in the first variable. So you can pull out a Z linear, so you can pull out a B. But C is also linear in the second variable, so you can push it to the other guy, and you get CAB. Yeah, so that tells you this. And then you can also check that theta is unique. Okay. So that proves that this tensor product is. If you do the tensor product with 0 module, then you always get 0 module. Okay. So yeah, so maybe I'm not in mood to. So one can do this. So If you are interested, you can look at the lecture on algebraic geometry. It's on YouTube. Yeah, so you can, if you are interested, you can go through this lecture. But I don't really want to do this in this generality for represent. It's like yeah, overkill. Yeah. So there are some basic properties which, if you are interested, you can study. And in that, so I can even tell you it's lecture 10. 9 and 10 are about, and 11 are about tensor products. Yeah. So you wouldn't need any algebraic geometry for that. But let me get back to representation theory. Yeah. So I'll do in this setup. I'll tell you what tensor product of vector spaces are. Yeah. So if you have yeah. So let so let let V and W be finite dimensional K vector spaces. Then then V tensor W. So one should put K, but people drop here. So I mean, in the ring case, one should do it more religiously, but even in the ring case, sometimes people drop it. But in field case, people certainly drop it because there's only one field involved when you're working with vector spaces. Yeah. So V tensor W is also a finite dimensional vector space. So any guesses what will be the dimension of, or how does this look like?
Like, it would be like the product of them.
It looks like my connection is bad. So can you repeat?
Yes, sir. So it would look like the product of dimension, say V has basis V1 to Vn and W has basis W1 to Wn.
Yeah.
Then it would be like the elements of the basis
yeah.
would be like V tensor W and so on.
Yeah.
Like that would be the product dimension would be the product of the.
Yeah, exactly. Yeah. So if so what happens is if V is say so V is not generated but basis. Yeah. So V is V has a basis V1 to Vn, and W has a basis W1 to Wm. Then V tensor W is is a vector space, has a basis so I'll write this, but you should question what this is. Yeah, Wj. So I should have done a little more on tensor product. I between 1 to n and j between 1 to n. Yeah. So So what is this guy? Yeah, VI tensor. So I have said it's this is a basis, but we should say what VI tensor WJ is. So what is VI tensor WJ?
These will just be the values of the bilinear map, right?
Yeah, that's right. Yeah. So this is why the bilinear map doesn't show up. Yeah. So this tensor product, because it's sort of inbuilt in the notation. So this tensor product comes with a bilinear map V cross W to V tensor W. V tensor W. So when someone writes VI tensor, the notation is phi of V comma W is some element of is an element of V tensor W. Is denoted by this guy. Yeah. So little V tensor little W is basically the image of this bilinear map. So it's the bilinear map. Yeah. So if you denote by these elements, so some of these elements so these pure tensors, which are called pure tensors, you denote it by this, then it's understood what the bilinear map is. Yeah. It's given by these. So of course, elements of this guy V tensor W is not just this. Yeah. These kind of elements are just the image of this bilinear map. There are many more elements. So sums of these. Yeah. So remember, if you remember the construction, V tensor W is quotient of the phi group over V comma V cross W. Yeah. So general element of V tensor W looks like summation Ri R summation R alpha V alpha tensor W alpha, where R alphas are in, so in this case in the base field K, and V alphas are in B. So this is a finite, yeah. So finite sums. I mean, whenever you do sum, it's always finite. So finite number of terms are there. So maybe I can remove this alpha. V alpha in V and W alpha in W. Okay, so this is how a general element look like. So not every element is of the form V tensors W. Okay. So this is a fact. This is not completely obvious that V tensor W has a basis like this. So yeah. So yeah. So maybe I should say something why this is true. So yeah, so of course I could go to the properties, but maybe for vector spaces this is clear. So of course this set is a generating set of V tensor W, yeah, because any arbitrary element of V tensor W you can write it as this guy, yeah. So note, let's call it B. So note that B generates V tensor W because any arbitrary element looks like this, and each of these V alpha, you can write it as k-linear combination of V1 to Vn. Each of this W alpha, you can write it as k-linear combination of W1 to Wm, and then of course expand it, yeah, because it's basically image of this bilinear map. Yeah. Okay, so maybe, yeah. So maybe, yeah. So I should maybe, since yeah, maybe I should say a little more about tensor product. Yeah. Otherwise, it's a bit silly. But this is the information you need, more or less. Yeah. So maybe I'll go back to this to that and say a few more things about tensor product. At least the properties of these little tensors and so on. Well, I can do it here itself. Yeah. So so some properties. So this since phi is bilinear, what you know is that V tensor W1 plus AW2 is same as maybe V tensor W1 plus A times V tensor W2, and similarly in the other variable for all V in V, W1, W2 in W, and A in the base field K. So so here, I mean, you can just cite it for modules, not necessarily for vector spaces, all these properties. V tensor 0, and this will tell you that V tensor 0 is same as 0 tensor W is same as 0. So this is the 0 element of this module, or this vector space. Yeah. So tensoring anything with 0, it gives you 0. And so this is the 0 of W, this is the 0 of V, and this is the 0 of V tensor W. Okay, so these are different vector spaces. Yeah. So and A tensor V A times V tensor W for A in K and B in W in V and capital V and capital W respectively is same as AV tensor W, and this is also same as V tensor AW. Okay, for all V in capital V, W in capital W, and A in K. So this I've just written phi is bilinear in this possibly complicated way. Yeah. So this is just the translation of phi is bilinear in this new notation. Okay. So now it should be clear that B generates V tensor W, and then you have to also show that they are linearly independent. Yeah. So so the point is, if you take some yeah. So maybe that I'll leave it as a homework problem. Yeah. So B is linearly independent. So I think maybe you can, but just using this property, you should be able to do it. Okay. So maybe I will go a little bit so that you have a feel of what tensor product is. Otherwise, there's no point in doing it in so much generality. Yeah, and then I was thinking of doing symmetric product, define tensor algebra or something, but it can wait. Yeah, there's no rush. Okay, so so these are some basic properties of tensor product. Yeah, So suppose R is a ring and A, B, C are R modules, then this R tensor over, then if you tensor it with R, then you don't get tensor this R module A with A, then these two are isomorphic. Yeah. In fact, you can say what the isomorphism does. So this, remember, R tensor A is going to be generated by these kind of elements, little r tensor little a, yeah, because arbitrary element looks like sums of this, yeah, with R coefficients. So once I tell you what happens on this generator, then it determines the map. So actually the map is R tensor A goes to R times A. Yeah. And it's sort of symmetric. So A tensor B is isomorphic to B tensor A, and the isomorphic, and you can actually, so not some arbitrary isomorphism. It's isomorphic in a way that the isomorphism sends A tensor B to B tensor A. Yeah. So natural isomorphism. Similarly, if you take a tensor of A and B with C, is same as first taking tensor product of B and C and then taking tensor with A. Okay, so this is the third property. And this fourth property, this is the important property which one can use to show that abstractly that V tensor W is a free module of dimension m times n. Yeah. So that is A direct sum B tensor with C is same as A tensor C plus B tensor. So there is a typo. Which no one pointed out. Yeah. So A tensor C direct sum B tensor C over R. Okay. And again, the map is sort of natural. Okay, so an element of A direct sum B is A comma B. Yeah, typically it looks like A comma B, and little tensor with C you send it to this. Yeah, so there is an isomorphism which will send this to this, and then there are some other properties which is not essential for this course. Okay, so if you use 4. Then also you can show, yeah, that this the vector the dimension of V tensor W is precisely m times n. Okay. So yeah. So maybe one of the proof. So the proof of 1 is same as this one. Okay, this example which we worked out, you can use the same proof. Okay, so maybe 2 we will do. I'll tell you the proof of 2, and then we will go to vector spaces. Okay. Yeah. So you want to give a map from tensor product is done in a careful way, yeah, because we don't understand the module that well in this using the construction. Yeah, the construction is crazy, so we don't want to go via construction. But the universal property tells us how to give a map from a tensor product. Yeah, so it's giving a map from a tensor product of 2 modules to another module is equivalent to giving a bilinear map from the product of those 2 modules to that third module. Yeah, because the universal property says that if you have a bilinear map, then then there is a unique map from the tensor product to that module, yeah, which will make that diagram commutative. So we want to show that A tensor B is isomorphic to B tensor A, and we want to give an isomorphism, but and we want to check that it's an isomorphism. So what one does is give a map from a bilinear map from A cross B, and that will give you a linear map from A tensor B to R. Yeah. So A cross B we know. A tensor B is not very. If we know A and B, then A cross B also we know. Yeah. So A cross B is some A direct some B. Yeah, same thing. So A comma B, you send it to the element B tensor A of R. Yeah, which is I mean, you know, this structure map. Yeah. So C2 of B. So B tensor A comes with this structure map. I mean, B tensor A is precisely the image of this bilinear. Yeah. So so you define C to be this guy, and then since phi2 is bilinear, linear in both the variables, C is just switching them. Yeah. So C is also bilinear. Okay. So by definition of tensor product, universal property of tensor product, there is a map theta from A tensor B to B tensor A, which is R linear, and which will make some diagram commutative. So such that theta composed phi1 should be same as C. So what does that theta composed phi1 do? It sends theta will phi1 of A comma B is precisely phi1 is this first structure map A cross B to A tensor. Phi1 of A comma B sends A comma B to A tensor B. So it will send it. So so what does the theta do? Theta sends A tensor B to B tensor. We don't know what it does to other elements, but for pure tensors, we know it does this. Yeah. So you have got a map theta from this to this. So one way to say that it's an isomorphism is, so one way is to say that it's surjective. I mean, it's surjective because it maps, so it's generated by B tensor A is generated by these guys. So it is going to be surjective. Injectivity will be tricky. So another way is, and so one has to try to do something. But another way is to give an inverse map. I mean, it's sort of the whole thing is symmetric, yeah. So similarly, you give a map theta prime from B tensor A to A tensor B, and then the advantage is you'll get something similar. Yeah, theta prime will send B tensor A to A tensor B. Yeah? And then if you compose these two, of course, it's identity on pure tensors. But pure tensors generate. Yeah, so these generate A tensor B. So that tells you that these both of the compositions are identity. Okay, so that proves two. Yeah, and yeah. So the rest I had anyway assigned homeworks and stuff. So except for 5. Yeah, so they are so all these proofs are in similar spirit. You sort of give bilinear maps and work with that. Okay, so so these basic properties help you figure out what tensor product is. So for instance, we will use this to show V and so that V tensor W is indeed same dimension as M times N. Yeah. So let me go back here. So, but I mean, you try to do it directly, try to show that B is linearly independent. But I'll just show, so if I show that the V tensor W has same dimension as M times N, that also proves that B is linearly independent because it generates. So let me try to prove this using those properties. So since V is of dimension what? N, and W is of dimension M. Since V is of dimension N, V is isomorphic to K power N. Yeah, and similarly, W is isomorphic to K power m as K modules or as vector spaces. We have that V is isomorphic to K power n and W is isomorphic to K power n. Yeah, now what do we get? So K power n, so V tensor W is isomorphic to K power n tensor W. Yeah. But what is K power n tensor W? So maybe I don't need the other isomorphism. So K power n, we can think of it as direct sum of modules. Yeah. So for two, so we can think of it as K direct sum K power n minus 1 tensor W. Yeah. But this, by definition, is isomorphic. By definition, by that property, we know is this is same as K tensor W, direct sum K power n minus 1 tensor W. Yeah, it's direct sum of these two base. But K tensor W, this is tensor over K. Yeah, so it doesn't do anything to W. Yeah, so this is the first factor is isomorphic to W. The second factor, now maybe you say by induction, this is isomorphic to, or you continue doing this as W power n minus 1. Yeah. So by induction, you try to prove that K power. So this is this. So what you get is this is isomorphic to W power n. Okay. Yeah. So that this implies V tensor W. So maybe this is. So here I'm also using induction, if you like. Induction. Okay. Induction on n. So V tensor W, dimension V tensor W is, so W is m dimensional, so W power n is mn dimensional. Right. Any questions? Okay, so yeah, so maybe yeah, so I don't know, this back-to-back classes will looks like it's going to be a little too long. I don't know if it's a good idea to do online classes this long. So what I'll do is I'll try to find a slot so that we have 3 1-hour class. Yeah, I mean I can do this, but I'm not sure if the concentration levels are going to be same. Yeah, so maybe you stop here today, and next week I'll try to reschedule. So we will do one of the hours now, and maybe another hour I'll try to reschedule for some other time slot. Okay. So that is somewhat easier. So let me stop.